I would like you all to start with a problem. So, everybody here, please think of a two-digit number. I want you to take the two digits in the number, and I want you to just simply add it. To take that sum that you just got, and I want you to subtract it from the original number. I want you to remember that result, and I want you to translate that into a table that I'm going to show with a lot of pictures. If I'm reading all your vibes correctly, I'm going to guess that you all saw the sun. This time, why don't you try another two-digit number? Something different from what you did last time. Once again, take the two digits, add them. Subtract that from the original number. Now take the result and translate it to the table. Now just for kicks, I changed the pictures completely this time. Okay? So, look at the box in which you see your picture. Well, all I see is happy faces. My name is Padhu, and I'd like to take you all with me through a mathematical journey in the next few minutes. I want to empower you with the simple message of why we need to promote the awareness of mathematics. I also know there's several in the crowd who are wondering what just happened. Well, it's all about the beauty of numbers, mathematics, patterns, and when you start to appreciate that, sometimes mathematics will start to look like magic. So let's go ahead and try another problem. A wealthy man who owns a lot of cars informs his three daughters in his deathbed that he will leave them with all his cars. To the eldest daughter, he leaves half his cars. To the second daughter, he leaves 1/3 of them. And to the youngest, he leaves 1/9 of them. Well, after he passes away, the three daughters went to get their cars, but discovered there were 17 of them. Now, they were all puzzled. Of course, 17? How would you make a half of it? How would you make a third of it? How would you make a ninth of it? So we need to help the daughters to solve the problem. I'm going to draw 17 cars, nicely gift wrapped, for the daughters to take. This is exactly where they make a call to their number one friend who happens to drive with his own car. Oh, look, there's 18 cars there. We can take half of it. That's 9 of them. Why don't we just give it to the first daughter? Well, let's take a third. There's 6 of them. Why don't we just give it to the second daughter? Oh, 9th of what you see there is 2 cars. Why don't we just give it to the third daughter? And off walks the number one friend. Problem solved. All of a sudden, we have solved the problem. So it is very important to understand to have an open mind to solve problems, and especially when you have real-world applications that do not often admit textbook solutions. To give you an example of a real-world application, on the top left corner, what you see is what you would see inside your head. It's what is called as the circle of Willis. And it is basically a fascinating network of arteries that go to different parts of the body doing different things. And if you look at it closely, there's a sac-like structure, which is a focal dilatation of the arterial wall, which is what is called as an intracranial saccular aneurysm. And these aneurysms sit there, and they start to grow, eventually rupture, and then the patient gets what is called as a subarachnoid hemorrhage, which leads to a stroke, and eventually 50% of them die, 50% of them get a neurological disorder. Now, what you see on the top 3 pictures are typical aneurysms. In the middle, you see an aneurysm that is connected to an arterial wall through a very narrow neck. You see an aneurysm that is connected to an arterial wall through a broad neck. On the left, you see an aneurysm that's fused with the arterial wall. Therefore, it's called a fusiform aneurysm. Now, on the left there, you actually see one of the gold standards for surgery, which expects the neurosurgeon to actually cut you open, and it requires the skill of a crafty surgeon to go in and actually place a metal clip. And once you place the metal clip, then the blood starts to do its own regular chores, not go inside the aneurysm and hit the walls, and that's one of the causes for the rupture. Now, yet another popular surgery is what is called as endovascular occlusion, and where you actually send in what is called as a thrombogenic wire and occlude that part. And the whole idea being the blood flow will start doing its regular routine. Now, you must be wondering, what is a mathematician doing with all this biological and biomedical engineering lingo? Well, I actually had to formally learn this when I was employed in a biomedical engineering program. And this is when I learned about how important this problem is. And about 2 to 5% of the population just in the United States harbor an aneurysm each year. About 18 to 35% of them harbor multiple aneurysms. And so there is no good news with aneurysms, as I just told you. But it was very interesting for me to be a part of this big group of biologists, of bioengineers, and who respected me for what I do, and who wanted me to actually give some input into the data interpretation of when something can go wrong. For example, when does an aneurysm rupture? Why does it rupture? How does it rupture? All these are mathematical questions. And so even the slightest information that I can give them back from analyzing the data is going to be very helpful in a decision making as a whole. And so this particular problem, I was funded by the National Institute for Health, and it actually gave access to so many students at all different levels. And actually what you see at the bottom left corner is Congressman Connolly. We had an opportunity to actually visit his office because one of the students who worked on this project, her project was selected by the posters on the Hill. And so we actually happened to visit lots of congressmen and talk about the importance of math and in education and health. And this is an example of a real-world application that does that. Mathematics also finds its way in all the other types of applications, like, for example, defense. Now, I served as a summer faculty fellow at the Air Force Research Labs a couple of summers, and that's when I learned about this problem. So what you see there is what is called as a micro air vehicle. It's literally about 6 centimeters in wingspan. And these vehicles are, were designed to actually for reconnaissance and military surveillance. Now they find a lot of other applications, like when there's a fire in the building, you can send these vehicles in, instead of sending the firemen in, because most of the deaths happen when the firemen go into buildings where there's no people. And so these vehicles can really help out in bringing back information. Now, the initial designs, of course, came with rigid wings. And later on, people looked around and they saw birds and insects doing such a wonderful job at going through obstacles and all that. And so next came flexible wings. Now, how does this problem interest me? Well, as a mathematician, when I look at this problem and the previous problem, to me, all I see is two things. I see a fluid in the last problem that was a blood that was going inside an arterial wall, which is a structure. And in this problem, I see a structure, which is the wing, which is actually deflecting around, and fluid is around it. So to me, all I see is a fluid and a structure. So all I have to do is go back to my differential equations and write down equations for fluids and write down equations for structures. So yes, we do solve equations to solve these problems when you solve the school simulations. But these are, for example, this is the Navier-Stokes equations, and you have linear elasticity equations. And so we try to understand how these equations interact and give back information, and how we can actually turn that into something that is usable. And that's what one of the areas that I work on is fluid structure interaction. So if I want to summarize the philosophy that I just talked about, you have a physical system, which could be modeling an aneurysm, it could be modeling a tsunami, or modeling a micro air vehicle. The first task is to convert that into a mathematical model. Now often, when we convert that into a mathematical model, it's sometimes easy to just go and find the solution in a textbook. But life is not that great. In most of the real world problems, it's so challenging that textbook solutions don't fly. So one has to come up with clever ways, which we call as computational algorithms and computational mathematics, where you come up with creative ways to solve the same problems. But the only trade-off is you don't get exact answers, you get approximate answers, which is okay. At least we get something that is reasonable. But the only thing is, you can't just take everything for granted. You need to check why your computational algorithms actually work. And the one way to check that would be to compare that against the analytical solution. So make the model simpler, then maybe you can find textbook solutions and try to see if your scheme that you introduce works. But to me, research is not complete if you just do the theory and get your exact solutions, and if you just do the practice and just do computational codes. You have to work with experimentalists. And that's when the circle of research is complete. So theory, numerics, and experimental work, when they join hand in hand, then we can solve bigger problems, like trying to understand Alzheimer's, trying to understand. So you can't just do something in the lab and try to figure out a gene and claim that you've done everything. You have to have a model that goes with it. You have to validate the model. And so if you want to validate the model, then you go back to textbook solutions. So it is a cycle that completes this research. But there is still a great need to motivate students to actually participate in this research. Motivate students to understand what STEM is all about. And like the message that you heard from the previous speakers, there is a great need for the next generation STEM workforce to participate in these types of problems to help solve real-world problems. So just to, from a recent report, American students scored 23rd in math and 31st in science when compared to 65 other top industrial countries. Now in math, the countries that are ahead include countries like Liechtenstein, Slovakia, Netherlands, Singapore. In science, these include countries like New Zealand, Estonia, Finland, Hungary. Now, I've always wondered, what is that these countries are doing different in motivating their kids to do math and science? And I've had conversations, lots and lots of conversations with administrators, with K through 12 teachers, with academicians, and lots and lots of different type of people. And after talking a lot with lots of people, I've come to believe that mathematics, for example, where at a very early age, somewhere it turns into fear. And that fear turns into hate when they come to college. And often that hate gets into their educational learning system, and students sometimes often lack fundamental concepts in making meaning of the mathematics they are using. Let me give you an example. So I already did that. So this is actually work of a student who was doing a big computation, and there was this one step that he had to do, which was 33 divided by 3, and so he just cancels the 3's and writes it as 3. So I exactly knew what he was doing. He was really doing this problem in his head, 3 times 3 divided by 3. But he just used something that he thought was correct. So I cornered him and I asked him, what's going on? And here's what he had to say. My middle school teacher taught me, if I see something on the top, if I see the same thing in the bottom, I cancel. Now, here's a student who has this half-baked idea of a rule that he has memorized, but he did not know how to apply it, when to apply it, where to apply it. But I'm actually glad that he had something in his head, but it's just that he did not apply it correctly. So I had to make a real-world connection. So I said, you and 2 of your buddies go to a bar, and the tab comes to $33. How much do you owe? He said, $11. I said, how did you do it? He said, I divided 33 by 3. I said, that's exactly what I'm asking you to do. So here's an example of a mistake that can be easily corrected. Okay, but I'm going to give you now an example of a mistake, which is not a simple mistake. And I'm talking about the Patriot missile failure. February 25, 1991, the American missile, Patriot missile in Saudi Arabia had failed to intercept the incoming Scud. Now it was actually due to a calculation error, which led to a computer arithmetic error. Now what actually happened was the internal system clock, which actually does the calculation in tenths of seconds, which needed to be multiplied by 10. So in a computer, 1 over 10 is represented in terms of binary, and this is how the digits go. But unfortunately, in a computer, it had that particular machine, for example, could only store, it was a 24-bit register. So it could only store so many digits, and the rest of them were chopped off. And because the rest of the digits were chopped off, there was an error in what was actually observed. This small chopping error translated into something in terms of the decimal system. I just went from the binary to the decimal system. And when it was calculated as a time in hundreds of hours, it led to about 0.34 seconds. Now, a Scud missile travels at around 1676 meters per second. Now, in half a second, it can actually go more than half a kilometer, which was beyond the Patriot missile's range gate, and the disaster happened. Now, I just wanted to give you 2 examples. One which could be corrected very easily. One needs a lot of research to understand what can you go and fix. How can you change the mathematical algorithms and understand how we could have fixed these types of things before it could have happened. So, but these are real-world connections. These are important things to teach in classroom. So I've often wondered, when we as educators go into a classroom and teach children, teach students, I've always wondered, does our teaching style match the learning style of the student? So, for example, I as a teacher, or other educators also, we all go into the classroom thinking, I'm going to make the students happy. I'm going to give them burgers. But then the students are sitting there and thinking, why is this guy bringing burgers every day? Why not pizzas for a change? It's that simple philosophy that causes the gap between our teaching style and their learning style. So what can we do to reduce this gap? Well, one of the solutions which has been practiced a lot now, and it's showing a lot of evidence, is problem-based learning. So for example, if I want to teach geometry, if I want to teach something about cost and budget and all that, you're seeing kids actually building tall structures. They're going to be talking about geometry, they're going to be doing stuff, and so they're actually doing hands-on work. If you want to measure the height of buildings, the height of trees, they're actually using bamboo skewers to tell exactly what the height of the building is. You don't need fancy technology. It's all about how you can do rational numbers and proportional reasoning, for example. What you're seeing down below is high school teachers who are actually humming into a device which is translating their hummings into waves. Now the next time when they actually teach some section in pre-calculus, they will actually use this as an example to teach the students what problem-based learning is all about. So things are changing, and for the good. So story in closing, this is about the number E. Now the number E is a strange number, and it is just like another number, famous number that you all know, pi, which is of course 3.141599265, and goes on 35897932. That's the best I can do. So, but it keeps going on. People can recite thousands of digits. Okay. Now you don't have a way to check because I just recited some numbers. I'm going to teach you in leaving the number E, which is also another famous one. Again, if you know about anything that has to do with exponential growth, exponential decay, everything has to do with this number E. So I'm going to teach you how to remember this. There's only two things that you need to know about Andrew Jackson. He was the 7th president of the United States. He was elected into office in 1828. I repeat, 1828. Like every good mathematician should know, the angles of an isosceles right angle triangle is 45, 90, 45. Like I said, you just need to know two things about Andrew Jackson. Now that's E for you, okay? But I shared this story with elementary students, and what really surprised me was they all came back to me and actually told me the rest of the story. So they actually did about 13 other digits, and I was surprised, the teachers were surprised, and they actually put a story like Andrew Jackson ate 35 ice creams every day and so on, and they just made up a complete story. But the beauty of this, it goes with my belief, is if you can put a story to the mathematics that you're doing, to the science that you're doing, problem solving is too easy, okay? So, and that's the whole idea. And if I want to leave with one message today, we as educators, it is highly true that most of us, we want to do everything in a traditional way. We want to take the textbook approach. We want to actually do formulas, and then go for the problem. So our philosophy of teaching has always mostly been, here is the mathematics, go solve the problem. Here is the science, go solve the problem. Here is this, go solve the problem. I challenge you all to think about reversing this philosophy into, here is the problem, find the mathematics to do it. If we can do that, we can engage, we can excite, we can empower anyone, the learning of any student. And with that, I'd like to also tell you that not only does it help students achieve their goals, but also we'll be able to enhance the next generation's STEM workforce. Thank you.